A nonlinear equation is an equation that has a degree higher than 1. The first nonlinear equation we're going to look at is that of a circle. If you look at these two equations, these are two different circles. In the first equation, the coefficient is the same value and both the x and the y terms are squared. In the second equation, both of the coefficients for the x and the y terms have the same value and both of the x and the y terms are squared. This is indicative of a circle. Now let's look at an ellipse. Note the difference between the circle and the ellipse. Both of the circle and the ellipse, the x and the y variables, are squared in all of those equations. However, with the ellipse, the coefficient for the x and the y are not equal. In the equations for parabola, you're going to have y is equal to some x squared term minus some integer or some rational number. You may or may not even have another x term to the first degree within that equation. Now, a hyperbola is going to look a lot like an ellipse. Your x square and your y square terms are not going to be the same. They're not going to have the same coefficient. But what's different between the ellipse and the hyperbola is that your x square and your y square are going to be subtracted. They're not going to be added. On an ellipse, they're going to be added, and on a hyperbola, they're going to have the minus sign between them. A nonlinear system of equations is a system in which at least one of the equations is a nonlinear equation. Now, it is possible for the plane that bisects your conic section, which creates these nonlinear systems, can touch, and so therefore you can get a line within a nonlinear system of equations. So let's do example 85.1. So here we have two equations. We notice that we have a circle for equation A because both of the coefficients are the same, they are 1, and we have x squared plus y squared. And then we have a linear equation where both the x and the y term are to the first degree. So first thing we need to do is we need to find out how we can relate these two. And probably the best thing to do is to solve for y in our linear equation, which is equation B, and then let's square that so that we can have something to substitute in for y squared. So now that we have solved, we know what we can sub in for y squared. Let's do that in that first equation A. So we sub that in, and then we do our squish, and then we're able to factor and find that x is either equal to 0 or 5x minus 12 is equal to 0. So now that we have x is equal to 0 or 5x minus 12 is equal to 0, we can solve for our second x term, which, as you can see, is 12 over 5. Now that we have those two x values, we can substitute them in for the y, which we solved for, which was y equals 2x minus 3. So when we put in 0, y is negative 3, and we put in 12 over 5, y is equal to 9 over 5. Now that we've been able to solve for both the x and the y values, the two x and the y values that we were able to find, we can see the 2 points of intersection between these two equations on this graph. Here's that graph illustrating this nonlinear system of equations. We can see the circle part of the graph, and then we can see the linear equation 2x minus y equals 3, and where it intersects the circumference of the circle at 2 points. And those are the 2 points that we solved for. I just wanted to make a note with 12 over 5 and 9 over 5 as our two xy coordinates for one of the points. Sometimes it's easier to see that on the graph if you go ahead and divide and get the decimal value. So let's look at example 85.2. We have another system of equations here, and we notice right away that we can use elimination because 5td and negative 5td will cancel each other out. And when we finish dividing, we end up with BTD is equal to 20. Now that we know that BTD is equal to 20, we can substitute that back into the original equation A, and we find that 5TD is equal to 5, so TD is equal to 1. We could take that value and sub it back into our BTD factors and find that B is equal to 20. So now we have both the values of B and TD. So let's review. We can determine the type of nonlinear equation based on the components of the equation. When we have a system of equations, we can manipulate one of the equations to allow us to substitute or use elimination to solve and substitute to find the value of the variables given. As always, thanks for joining us at Jupiter Math. For more information about our math programs, contact learning@edugraphics.com.